Hello everyone, I'm T, a certified flight instructor, and welcome to this deep dive explainer. Today, we're going to absolutely master the uncompromising details of aircraft construction, certification, and aerodynamic physics. Because, look, if you're serious about aviation, you already know that flying is so much more than just yanking on a yoke and stepping on a rudder. It's about developing a really profound, comprehensive understanding of the machine you're operating and those invisible forces acting on it. We are going to dive deep into the FAA's guidelines to unpack the rigorous standards that keep us safe up there. So get ready. We're leaving literally no technical term, no numerical value, and zero safety warnings behind. As your flight instructor, I need you to understand this syllabus top to bottom. We'll be moving through 6 main areas: certification and airworthiness, the 4 aerodynamic forces, aircraft axes and stability, the fuselage and wings, empennage and flight controls, and finally, the landing gear and power plant. All right, let's just jump right in. Section 1, certification and airworthiness. Because before we even think about touching a flight control, we absolutely must understand the legal bedrock of aviation. Okay, what's really fascinating here is just how specific the FAA gets with its regulations under Title 14 of the Code of Federal Regulations, or 14 CFR. I actually want you to memorize these numeric codes. So if you're flying a standard training airplane, something in the normal, utility, or acrobatic category, that falls strictly under 14 CFR Part 23. But say you step onto a massive commercial airliner. That transport category airplane is governed by Part 25. Rotorcraft, they've got their own specific rules under Parts 27 and 29. Manned free balloons sit at Part 31. And it doesn't even stop at the airframe itself. Aircraft engines are fiercely regulated under Part 33, and the propellers under Part 35. These highly precise, compartmentalized regulations, they are literally the blueprint that guarantees your safety in the sky. Now, once an aviation product actually complies with those extensive CFR standards, the FAA issues a type certificate. But what comes along with that is arguably even more crucial for mechanics and pilots, and that's the Type Certificate Datasheet, or TCDS. You can pull this document right off the FAA website, and you can think of it as the ultimate mechanical blueprint for safe flight. It spells out every single crucial design limit and operational characteristic for that specific aircraft engine or propeller. Without the TCDS, we honestly wouldn't know the exact parameters that were engineered to keep the aircraft structurally sound in the first place. So how does all this legal paperwork actually translate to your daily flight operations? Well, during your required pre-flight conformity inspection, you absolutely must locate the airworthiness certificate on board. And I want you to notice the stark visual difference between the white and pink certificates we're looking at here. Standard airworthiness certificates, the ones printed on crisp white paper, are issued for your normal, utility, acrobatic, commuter, and transport category aircraft. On the flip side, special airworthiness certificates are printed on pink paper. These are strictly reserved for primary, restricted, limited, light sport, or experimental aircraft. Here's a pro CFI tip for you. If you get into an airplane and see a pink certificate, your operational limitations are going to be vastly different, and you need to know exactly what those restrictions are before you even think about turning the key. Oh, and remember, that certificate, it's only valid as long as all the required maintenance and inspections are rigorously kept up to date. Moving right along to Section 2, the 4 aerodynamic forces. With the legal paperwork out of the way, let's step into the invisible physical environment where these incredible machines actually operate. This diagram brilliantly illustrates the delicate, almost magical balance of flight. When you're in straight and level, unaccelerated flight, you are constantly managing this perfect dynamic equilibrium of 4 distinct forces. First up, you have thrust. This is the forward force produced by your power plant and propeller, and it has to perfectly overcome the rearward retarding force of drag, which is basically just the disruption of airflow caused by the wings, the fuselage, the antennas, all of it. Opposing those two is lift, created by the dynamic effect of air acting perpendicular to your flight path right through the wing's center of lift. And lift must perfectly oppose weight, which is the combined relentless downward pull of the aircraft, the crew, the fuel, and the cargo through the center of gravity. It's a tug of war, really. If any single one of these 4 forces changes, your aircraft is instantly going to accelerate, decelerate, climb, or descend. All right, Section 3, aircraft axes and stability. Because your aircraft operates dynamically in 3-dimensional space, manipulating those 4 forces requires absolute precision. Building directly on those aerodynamic forces we just talked about, any control input you make on the flight deck causes a rotation around one of 3 invisible axes. Let's break them down. If you pull back or push forward on the yoke, you're pitching the nose up or down along the lateral axis.
That's the imaginary line running straight from wingtip to wingtip. Now, if you turn the yoke left or right, you are rolling along the longitudinal axis, which runs horizontally from the nose all the way through the tail. And finally, when you step on the rudder pedals, you're yawing the nose, left or right, around the vertical axis, running straight up and down through the cabin. But here's the absolutely crucial detail. All three of these axes intersect perfectly at a single point, the aircraft's center of gravity, or CG.
And that brings us to one of the most critical safety warnings in all of aviation. Pay close attention here, because miscalculating your center of gravity can absolutely be fatal. The CG is the precise point where the entire mass of the aircraft centers. And here's the kicker. As you burn fuel during your flight, fuel that's situated away from the CG, that center point physically moves, which constantly alters your flight stability. If your CG is loaded too far aft, meaning too close to the tail, the aircraft becomes dynamically unstable. The terrifying risk here? If you enter a stall, you physically will not have enough elevator nose-down force to lower the nose and recover. It's a helpless situation. Conversely, if your CG is loaded too far forward, you create a severe nose-heavy condition. The risk there is that you might arrive at your runway only to realize you don't have enough elevator nose-up force to flare the airplane for a safe landing. You literally have to calculate this meticulously before every single flight, no exceptions. That leads us to Section 4, the fuselage and wings. Let's begin our detailed virtual walk-around of the physical hardware, starting right with the central structures.
So the fuselage is the main central body of the airplane, right? It accommodates the crew and provides the critical structural connection points for the wings and tail. Now, older, vintage training aircraft often use this heavy open truss structure made of welded steel or aluminum tubing. But modern aviation engineering has seriously evolved. Today's planes typically use a highly efficient monocoque, which is actually French for a single shell, or a semi-monocoque design. In a monocoque structure, the aircraft relies almost entirely on its meticulously riveted outer skin to carry the primary structural flight loads. It's incredibly clever because it drastically reduces the weight of the aircraft while maintaining just immense structural strength. Now, the wings attached to that sophisticated fuselage can vary drastically depending on what the aircraft is actually designed to do. Take a look at the two aircraft we have here. On the left, we've got a standard monoplane featuring just a single set of wings. Notice how it uses those external semi-cantilever struts. Those metal bars attaching about halfway out on the wing, those transmit the immense aerodynamic flight loads directly into the main fuselage structure. Then, over on the right, we have a classic biplane, which uses a much more complex, dual-lifting surface design with two sets of wings. And just as a side note, some modern low-wing aircraft use a full cantilever wing, which is engineered completely without external struts, carrying all those massive structural loads internally.
So what exactly is inside those wings carrying all that load? Well, underneath the thin aluminum or composite skin, you've got these robust structural spars running lengthwise, along with ribs that give the wing its exact aerodynamic shape and thickness. Plus, these spaces often house your fuel in integral tanks or flexible bladders. Now, if we look at the trailing edge, the back of the wing, we find two absolutely critical control surfaces. From the midpoint extending outward toward the wingtips, you have your ailerons. These move in opposite directions to alter aerodynamic forces and give us our longitudinal roll. Then, from the midpoint extending inward toward the fuselage, you have your flaps. When you deploy flaps simultaneously downward, they massively increase the lifting force of the wing. This is what allows you to fly at much slower, significantly safer airspeeds during your takeoffs and landings.
All right, Section 5, empennage and flight controls. Let's move all the way to the rear of the aircraft, where we find the critical structural tail group. As a practical CFI tip, I always tell my students, pay exceptionally close attention to your tail design during the pre-flight walk-around. Some aircraft have fixed horizontal stabilizer with a movable elevator hinged right to the back of it. But if your aircraft doesn't have a separate elevator, you're looking at what's called a stabilator. A stabilator is a massive one-piece horizontal tail surface that pivots entirely from a central hinge point. Because moving that entire surface creates such massive aerodynamic loads, stabilators are equipped with something called an anti-servo tab extending across the trailing edge. This little tab actually moves in the same direction as the trailing edge to intentionally decrease sensitivity. It acts as a counterforce to help you manage those really heavy control pressures when you're pulling back on the yoke. Breaking down the rest of the empennage, you generally have your fixed, vertical, and horizontal stabilizers doing the hard work of keeping the aircraft flying straight. Attached to the back of the vertical stabilizer is your rudder, which you operate with your feet to yaw the nose left and right. Attached to the horizontal stabilizer is the elevator used to pitch the nose up and down.
But listen, arguably the most underappreciated component back there is the trim tab. Trim tabs are these small, movable portions on the trailing edges of your control surfaces. Mastering the use of these tabs from the flight deck is an absolute game changer. By making tiny, incremental aerodynamic adjustments with the trim tab, you completely relieve heavy, constant control pressures on the yoke. It literally eliminates pilot fatigue on those long cross-country flights. Finally, Section 6, Landing Gear and Power Plant. This last section covers the physical components we use for ground interactions and for generating our forward thrust. Down on the ground, your wheeled landing gear typically consists of 2 main wheels and a third directional wheel. If that third wheel is mounted at the rear of the airplane, it's called conventional landing gear, though we all just call it a tail wheel. And let me tell you, tail wheel flying demands immense respect and incredibly precise rudder control from the pilot. If you're sloppy, the aircraft's center of gravity can swing entirely around on you and cause a highly destructive ground loop. Conversely, if that third wheel is mounted on the front, it's called a tricycle gear with a nose wheel. Regardless of which setup you're flying, you'll steer the aircraft on the ground using the rudder pedals, or in certain aircraft by applying differential braking to the main wheels. So, let's put this all together. We've built the monocoque fuselage, we've attached the strong cantilever wings, and we've secured the empennage to the back. But what incredible feat of engineering actually creates the massive thrust required to overcome the crushing force of drag and initiate the sheer miracle of flight? Well, that brings us right to the power plant. Securely housed within a streamlined air-ducted cowling or nacelle, which is specifically designed to force cooling air directly over the hot engine cylinders, is your engine. And here's the thing, that heavy engine isn't just sitting there to spin the propeller. It is literally the beating heart of your aircraft's survival systems. It generates the electrical power needed to run your avionics. It spins a pump to provide a critical vacuum source for your gyroscopic flight instruments. And in most single-engine airplanes, it provides the absolute vital source of cabin heat that keeps you alive in freezing temperatures at high altitudes. And bolted to the front of that engine is, of course, the propeller. Now, a lot of people misunderstand the propeller. It is definitely not just a big fan. Your propeller is literally a twisting wing. It functions exactly as a rotating airfoil. As the engine spins this airfoil, aerodynamic physics take over. A massive high-pressure area is formed at the back of the propeller blade, and a corresponding low-pressure area is produced right at the flat face of the propeller. This resulting immense pressure differential creates real aerodynamic thrust, violently pulling the entire heavy structural mass of the airplane forward through the air. It's an incredible piece of physics. So from the rigid, uncompromising legal standards of a Part 23 certification, to precisely calculating the exact moment arm of your center of gravity, all the way down to those invisible high and low pressure gradients swirling over your spinning propeller, this exact mechanical and aerodynamic synergy is what dictates every single flight. Having a thorough ground school knowledge isn't just about memorizing facts to pass a written test. This depth of understanding is exactly what separates a successful routine flight from a tragic, completely unrecoverable emergency. Knowing that a simple miscalculation, literally just a fraction of an inch in your center of gravity, can completely strip away your physical ability to recover from a low-altitude stall, well, I want to leave you with this final provocative thought. Every single CFR regulation, every aluminum spar inside that wing, and every calculated aerodynamic limit exists for one reason, solely to keep you alive. So do you possess the rigorous discipline and deep knowledge required to truly command these forces? Or will you just sit there and let the aircraft fly you? Think about that long and hard before your next pre-flight. Thanks for joining me on this explainer, and safe flight.